Good day, everybody, and we are live. So, in this chapter, we are going to take a look at the organic compounds, specifically alkanes, because they are kind of foundational to various organic materials, and it makes sense to start our exploration of introduction to organic chemistry with alkanes. But now just a little bit of differences between the inorganic and organic compounds. As you can see, so we're just going to rely on the slides that accompany these like video lectures. So as you can see from the slides that are in front of you, if you are enrolled in this course, of course. So we can see that organic compounds and inorganic are quite different, right? And one of the major differences that we are going to also take a look at is from the structural perspective, right? So previously we were looking at, for example, various salts such as sodium chloride, if you recall examples of inorganic compounds, right? So yeah, maybe these are some kind of like more complicated salts, such as maybe, I don't know, potassium sulfate. But now we're going to look at the whole new different composition that organic compounds are going to follow. And specifically, it is about the carbon, right? So carbon that we're going to have, it's going to be marked as C. So in organic chemistry, carbon is tetravalent. So this is going to be the prevalent kind of like valence scheme that we will have on a carbon in organic compounds. So basically, what does it mean? It means that the carbon has to have four bonds, right? So in alkanes specifically, we are going to have a carbon surrounded by four single bonds. So that's what I need to emphasize, because as we will later on see, some carbons can be surrounded by different combinations of single, double, and triple bonds. But what's going to be true about all the carbon atoms in organic compounds is that they will all be tetravalent, meaning that they will be able to make four bonds, right? Obviously, those bonds need to be bound to something, right? Such as maybe other carbons, right? Such as here, for example. So we can maybe connect two carbon atoms together. And now, guess what? We are trying to build a fundamental carbon chain, right? So maybe we can do something like this. So maybe in this case, we're going to connect three atoms together. And then what's going to be good about and exciting about this is that those carbon atoms can be connected into huge chains, maybe 100 carbon atoms, maybe 1,000, and so on, you name it. Right. So what's going to be true about organic compounds is that they will be looking something like that. I mean, specifically alkanes, and they are known as hydrocarbons as well, right? So what does it mean? What do I mean by this? It means that they are going to consist of atoms of C, carbon, and hydrogen, right? And that's going to be something like that. So we have an example of a typical alkane right here in front of us, right? So, alkanes are examples of hydrocarbons. They only contain carbons and hydrogens in their structure, right? Specifically for alkanes, we will have the situation in which case we are going to have carbons and hydrogens only and single bonds only. So there are no double or triple bonds because those cases will be true about other classes of organic compounds. So now let's take a look at some examples of alkanes. So this is one here, right in front of us. So that's going to be the alkane that has three carbons in its structure. Of course, we are going to have more various classes of those compounds, right? More examples of alkanes. But now just to kind of switch gears a little bit, let's take a look at some other hydrocarbons that exist out there. So for example, in addition to alkanes, we can also encounter such compounds as alkenes. Alkenes have a little bit of the distinction between, like, as opposed to alkanes. Alkenes will have to contain the double bond, right? And then you can see some examples in your lecture slides. For alkenes, alkenes will be looking like this, right? So in this situation, we're going to have, for instance, also the hydrocarbon, right? But then what's going to be true about this hydrocarbon is that it will have to have the carbon with one double bond and two single bonds, right? So that's what we have to have for alkenes. So in case of alkenes, we have a carbon that contains also total of four bonds, right? So, but we have a double bond consisting of two single bonds, essentially, and we have two separate single bonds. So next in line for hydrocarbons will be so-called alkynes. So bear with me a little bit here as I'm trying to navigate through that stuff. Okay, so now we're going to alkynes, right? So there's another example of hydrocarbons. So it's going to be looking something like this. So in this case, so what's going to be peculiar is that we are going to see the triple bond present in alkynes, right? So basically in alkynes, we're going to have a carbon, probably a few carbons, right? So connected to one another in a specific fashion. So, and then the alkyne carbon must have a carbon with a triple bond. If you look at the triple bond, it consists of three single bonds together, right? And one single bond will also have to be present on the alkyne type carbon, just like that. So here we have the alkane type carbon, which is going to be the carbon with four single bonds. And we also have the alkyne type carbon, which is a carbon with one triple bond and one single bond. So here we also have another alkyne type carbon, which contains a triple bond and a single bond, right? So what's going to be true about alkene, alkynes, and then alkane carbons is that they will all have four bonds total, arranged in various fashions around those specific carbon atoms, and they will all be tetravalent, essentially. So, moving on, let's take a look at the notion of functional groups, right? So, functional groups which are based off hydrocarbons can be represented by four different kinds. As you can see, these are alkanes, alkenes, alkynes, and aromatics, right? So we previously just took a look at some alkanes. So here are some more examples. So maybe you have an alkane with only two carbons in its structure, right? And then what's going to be peculiar here is that those carbons must have all single bonds. So we'll have like alkane functional group. Then we also can have the alkene functional group, which will be looking like this. So maybe we're going to have two carbons connected with a double bond, right? So then we'll have like the respective number of single bonds on those carbons. And then maybe we are going to have hydrogens only because we are dealing with hydrocarbons, right? So in this case, we have an example of the alkene functional group. So basically what you're going to look for is you're going to look for the carbon with a double bond connected to other carbon, right? So, or hydrogens. So that's what we are going to look at. So basically for alkenes, make sure that you are going to find out the carbon with a double bond, two single bonds, and then what's going to be also true is that this carbon with a double bond must be connected to another carbon atom, right? Not oxygen, not nitrogen, for example, but to another carbon. So basically, we're going to have in alkene functional group the carbon-carbon double bond, as they call it. So then for alkyne functional group, we're going to, guess what? Look for the carbon with a triple bond that is connected to another carbon, right? So something like that. So then we might have maybe here some hydrogens, right? Maybe another carbon, like this with three hydrogens on it and so on, right? So maybe we'll just fortify it with hydrogens here. So what's going to happen next is that you are going to identify an alkyne functional group, which will contain the carbon with a triple bond, right? And then this carbon must be connected to another carbon as well. So not nitrogen, right? Potentially that can happen, but this will make a functional group different from alkynes, right? So here we go. This is alkyne. So we have a carbon with a triple bond connected to another carbon. And then here, oh, actually, I made a mistake. I made way too many hydrogens here. So now it's proper, right? Right, that like that right here. So because why? Because we must follow the tetravalent carbons, right? So right now we are in good shape. So because this carbon is tetravalent, this carbon is tetravalent as well. They both have four bonds total surrounding them, right? Not five. Five is a grave error. Don't make this. I made it just now for you, specifically to kind of draw your attention to that. So, but don't make it in the future because I made this error for you. All right, so carbons must be tetravalent no matter what in hydrocarbons, right? So here we go. So that's the alkyne functional group right here, right? So you look at this hydrocarbon, okay, check. So on the carbons, hydrogens are present. So we have a triple bond between carbons, check. So we have the alkyne functional group. Finally, we have a very special case of the hydrocarbon functional group, which is called an aromatic functional group, and it will be looking something like that, right? So it's a very specific combination which distinguishes aromatic functional groups. So what do we need to have for that? We need to have the six carbons, right, attached to one another in a particular fashion. So here we have six carbons. They are in a cyclic form. They're all connected, so with at least one single bond, right? So, but now what happens next is that they will have the alternating double and single bond. So here we have a double bond, right? Single bond, double bond, single bond, double bond. So here we go, right? So in this case, if you see something like that, the combination of carbons and hydrogens, right? In which case the six carbons are arranged in a cycle and they have the alternating double and single bonds. Specifically, this formation, just look at the drawing. That's why we draw it here, right? So it's not gonna be all of a sudden maybe like 7 or 8 carbons, right, attached somehow to one another with the double and single bonds. Not 5 carbons, not 16. It's specifically 6 carbons. It's called hexagon. Hexagon, right, 6 carbons attached to one another with alternating double and single bonds. There are no triple bonds, no things like that, right? So just be aware. So it's a very specific combination of carbons that will make the aromatic functional group possible. And what could be done is that there could be different variations of aromatic functional group. So for our hydrocarbons sake example, we can draw something like that. And here we have it, right? C6H6, that's going to be the first representative, the very fundamental example of an aromatic function group. So basically, it's a hydrocarbon that contains this peculiar aromatic functional group consisting of 6 carbons connected to one another with alternating double and single bonds. And of course, hydrogens are attached to those carbons, right? So that's it. That's all we can do for the aromatic functional group when we look at the very first representative of the aromatic compounds, because as you can see later, so those hydrogens can be substituted. This is going to be a word that we're going to use a lot. So because it will, guess what? It will pave way to new compounds. Let's imagine you are going to substitute, for example, hydrogen here to, let's say, chlorine, right, atom. And then you are going to have a whole different compound, right? It's going to be very similar to this current C6H6, but at the same time, there will be no H, there will be chlorine instead of H. And then you have something similar yet different because you have a different atom instead of hydrogen, right? That you kind of like hypothetically remove in your brain, right? And then switch it to the chlorine. So now you have a similar but different compound because you have a whole new atom switched to the previously present hydrogen over there. So things like that, substitution will be like all the rage down the line, so to speak. So what else? Saturation. So alkanes that are like this. So I'm just looking at some examples of alkanes, right? So they are known as saturated compounds. So they have only single bonds and carbons and hydrogens. They are saturated hydrocarbons. So if You look at alkenes, for example, or alkynes or aromatics, they are going to be called unsaturated compound because theoretically those double and triple bonds can be broken in a very specific fashion to add, let's say, more hydrogens and saturate, for example, alkene with more hydrogens to turn the unsaturated alkene to an unsaturated alkane. But it's going to be done through specific chemical reactions at which we're going to be looking at later in the respective chapters related to this course. So now let's take a look at the notion of geometry, right? So we are going to take a look at some kind of like zoomed in details and zoomed out in this chapter. So we'll kind of be switching gears a little bit. So, but that's how it is. In organic chemistry, it could be quite kind of rife with various details. So let's go with that, right? So let's look at the notion of geometry, right? So there is a specific arrangement of the atoms around the typical carbon in alkanes, right? So let's take a look at some kind of representative of alkanes, such as probably methane, as you can see, right, in one of your slides. So methane will be looking like this. This is CH4, right? So that's the molecular formula of methane. And then if we want to do the geometry of methane, it's going to be looking something like that, right? What's going to be true about the methane is that it will have this central carbon right here, surrounded by 4 hydrogens. So 4 hydrogens will be connected to the central carbon, right? So the in saturated hydrocarbons, all the carbons will be similar, right? So they will be basically the same geometry-wise. What do we mean by geometry? Geometry is going to be the arrangement of those hydrogens, right, and the bonds rather around the carbon, right, in alkane specifically. So here we're looking at the so-called tetrahedral geometry, right? So the geometry shape of this will be tetrahedron, right? If that is a noun, so the adjective is tetrahedral, so you can say it is a tetrahedron or tetrahedral arrangement of the atoms around the carbon will be true in atoms or in molecules of alkanes. So the bond angle between the bonds right here will be about 109.5 degrees, and it's going to be the same angle here, here, and there as well. So we'll basically have about what looks like several angles, right? So that can be found between the CH bonds, and all of them will be about 109.5 degrees, right? So that's what is true about the tetrahedral geometry in alkanes specifically. Okay, so let's move on now to some more exploration of the functional groups, right? So in addition to alkanes, what you are going to see and alkenes, alkynes, and aromatic compounds, you will see more functional groups, right? So more functional groups means a larger variety of atoms in organic chemistry compounds. What do I mean by that? If we look at our slides that accompany this video presentation, you will see for example, alcohol functional groups, right? So which will be looking something like this. So we must have the carbon attached to the oxygen, and oxygen has to be attached to a hydrogen atom, right? So this carbon can have a variety of things attached to that. So maybe it's going to be 3 hydrogens. That's possible. Maybe instead of those hydrogens, you will have carbons attached to other hydrogens in turn. So because we are going to have a variety of different alcohols. But what's going to be true is that if you take a look at the alcoholic functional groups or alcohol, you are going to have a specific combination of atoms, right? Such as here we have COH, right? So pay attention. Here we have the carbon, which has 4 single bonds, right? So it's not like an alkene carbon or alkyne. It has to have 4 single bonds in the molecules of alcohols. Then we have the carbon-oxygen single bond, and we have oxygen H single bond. So this has to be like that, right? So there is a specific arrangement of atoms that is a signature of a particular functional group, right? It cannot be somehow randomly switched to some like other atoms, right? So even though they are similar, but we cannot have this switch, right? So we cannot switch this oxygen to, let's say, sulfur, for example, all of a sudden and call this an alcohol, right? So no, even though, yeah, the structure will be similar, maybe hypothetically we'll have carbon, sulfur, H, so it's not going to be the same, right? It's not going to be an alcohol functional group anymore. So pay attention to the composition of specific functional groups, and this is something that it's like best to memorize, right? And then not deviate from that. So then what else do we have? In addition to alcohols, we have some derivatives of alcohols. They can be obtained chemically from alcohols, and these are ethers, right? In case of ethers, we're going to have carbon, right, connected to oxygen, connected to carbon, right? And here maybe we'll have some other atoms attached to the carbons in this case, right? So maybe we'll have hydrogens, maybe we'll have other carbons, whatever it might be, right? So we'll take a look at more examples as we travel in this journey. So in this situation, you are going to have carbon, single bond oxygen, single bond carbon, right? So specifically, and then not like anything else. So that's the combination of carbons that you are going to pay attention to, carbons and oxygens, in order to identify the ether functional group. So basically, if you see something like that, so in that case, you are going to encounter an ether functional group, right? So typically in ethers, we are going to have the tetravalent carbon with 4 single bonds, right, attached to another carbon, another oxygen here, right? And then the oxygen atom will be attached to another carbon with a single bond. And then that carbon will also typically have 4 single bonds. Of course, there could be some kind of like more special cases, more advanced cases of ethers, but for now, we are going to concentrate on this specific arrangement of carbons, other atoms in these functional groups, such as oxygen, and the bonds, right? So that we will have in this functional group. So then moving on, so some other functional groups that we will encounter in our journey will be amines. So for amines, we're going to have nitrogen with a couple H's typically, right? So, and that's what we are going to have for amines. So maybe we'll have some examples of amines. So, but for amine, we're going to have the nitrogen, right? That's a requirement, which is attached to the carbon, right? So that's going to be our amine example. Those carbon has bonds, so which are attached to other atoms of some sort, right? And then the nitrogen has 2 H's. So sometimes instead of H, we might have something else, right? So maybe we'll have here some other groups, such as, or other atoms, right? So let's imagine we're going to have not H, but a carbon here with other atoms attached to that. So that's also a possibility. So that's going to be true about amines. Amines will be looking like that. So basically, we'll have carbon, nitrogen, and bond, right? So it's going to be specifically a single bond between carbon and nitrogen, not a triple, not a double bond. And then we'll have the typically single bonds from the nitrogen leading to couple hydrogens total in this case. So that's going to be an example of the amino group. And I will have at some like other variations of amino groups as well. So maybe if you want to have a look at some specific compound, just attach hydrogens, right? So then you'll be in a good shape to show an example of an amine.